Chapter 10, Harmonic Motion and Elasticity. This chapter consists of different topics. First, we're going to go to the ideal spring, energy of simple harmonic motion. Second, we're going to go to the damped harmonic motion and we'll study a bit about pendula, simple and compound. In topic 3, we go to driven harmonic motion and resonance. Finally, we go to elastic deformation in section 4. As an introduction before we start, it's important to know that these videos are intended just for the procedural work. We just focus on the mathematical process of solving problems. We will go a bit towards the physics, but we will not indulge a lot in the details. For further knowledge about the concepts, you can check YouTube. There are a lot of videos about that. It's important to keep in mind that these videos are intended for mathematical procedural work. First topic we start with is the ideal spring energy of simple harmonic motion. So as an introductory video, let's start with a simple simulation in which demonstrate what simple harmonic motion is. Simple harmonic motion is simply motion under the influence of a restoring force. What's meant by a restoring force? It is simply a force that pulls the body back to its equilibrium position as it moves away from it. And as it approaches the equilibrium position, it pushes it to the other direction. So it's always acting against the displacement. Over here, we have what's known as the horizontal elastic pendulum, consisting of a spring of stiffness constant K and attached to it a block of mass M. Here we've chosen M to be 0.1 kilogram and K to be 1. These are just values that we've chosen to produce this simulation. Now, moving the box a bit, you notice that we have displacement in green and the force in red. We all remember that F equals ma, so acceleration is also represented by the red vector here. You notice that the displacement and the acceleration always have opposite senses. This is a very important thing for simple harmonic motion, the motion under the influence of a restoring force. Now, we can observe the displacement, the force. I can also click here to observe the speed vector as well. So it is shown in the figure above. You notice that the speed admits an oscillating behavior, and this will all be discussed when we go to problems. Another thing which is important here is to study the energy of this oscillator. Energies involved are kinetic energy, half mv squared, and elastic potential energy known as half kx squared. Sorry for that. We also can produce the mechanical energy, which is over here conserved because there are no damping factors, and this will be studied later on. So that's it. Let's go now to check some exercises. Before we go to the exercises, we check the mathematical equations that we need to be aware of. So first, simple harmonic motion is the oscillatory motion that occurs when a restoring force of the form F equals minus kx acts on the object. This is known as Hooke's law if you remember it. Angular frequency is given by omega, which is 2 pi f. F is frequency, and that also equals 2 pi over t, which is the period. Remember that the period should be expressed in seconds, while frequency should be expressed in hertz. On the other hand, omega is in radians per second. The position time equation of an oscillatory body or motion is given by x equals plus or minus x max, cosine or sine omega t plus phi. Usually you notice that this phi, which is known as the initial phase, is to be dropped. Maximum velocity is given by the equation Vmax equal x max times omega. We do not need to go into the details of how velocity is derived. It's simply the derivative of x. Acceleration is related to position by the relation a equal minus omega square x. This gives a max being minus omega squared x max. Now, since a max and x max are values, we can drop this minus and say that a max is nothing but omega square x max. The negative sign drops if you're dealing with amplitudes or values. For a spring oscillator, which is this case that we studied, omega is square root of k over m. This is something we need to memorize. Elastic potential energy is given by half kx squared. Kinetic energy is given by half mv squared. Now, some knowledge about the energy and the graphs. The motion variables are x and v. Here we've chosen x to be x max sine. On the other hand, v becomes v max cosine. Notice the graphs. For x it starts from 0, for v it starts from maximum. This is something important. Whenever we have v max, x is 0. Let me change the color here. And whenever x is max, v is 0. Now the period is the duration from here to here, and it's the same for both. Now period is given by t, 0 or simply t, and don't forget, t is always 2 pi over omega. V max is omega times x max, we've written this. Passing to energy, since energy is half kx square or half mv square, it's always positive, so you notice the oscillation to be only on the upper and positive part. Mechanical energy is the sum of both, and if there's no damping, the mechanical energy is going to be conserved. The period for energy is half the period of the regular oscillation. That's because in one cycle, positive values and negative values of x or v would produce the same energy. That's why you notice the graphs of energy are squeezed more closer to each other, and the period for energy is half the period of a proper oscillation. So notice, T of energy is half proper period. And that's it concerning what we need to know. Now we pass to problem solving. A body of mass m is attached to a horizontal spring of stiffness k. The body oscillates without friction and its maximum speed is 1.82 meters per second, while its maximum acceleration is 4.30 meters per second square. What is the duration between the instant achieving the maximum speed and the next instant when the acceleration attains its maximum? Now, reading this application or this question, we have different ideas we need to be acquainted with. First, we are given Vmax. Let me write the given data on the side here. So we are given, let's write here the given. So Vmax is given to be 1.82 meters per second. I forgot the 2, let me add it. A max is 4.30 meter per second square. Now these two will help me a lot, but later on, once I determine what I need to find in the first place. The question asks about duration between the instant of achieving maximum speed and maximum acceleration. Now we know that maximum speed, Vmax, can be related to x max or x being 0, right? We know that Vmax occurs when x is 0. But we have nothing to do with acceleration. On the other hand, we know that acceleration is minus omega squared x, as we have seen before. So indirectly we can say that Vmax corresponds to x being 0 and thus corresponds to a being 0. So Vmax is similar to it, to a being 0 as in acceleration. Then reaching a max, that is x max, we know that this is equivalent to it, to v being 0. We know from the energy graphs, when kinetic energy is maximum, elastic potential is minimum. That is, when v is max, x is 0 and vice versa. So now we need to find the duration between v being maximum and v being 0, or simply a being 0 and a being maximum. That is, if we are oscillating, if this is a spring, and it needs to oscillate from 0 to max, the duration from here to here is nothing but a quarter of a period. Because we know that the spring balance, or the spring, is going to go in a quarter of period there, another quarter, continuing the other cycle in 2 quarters, giving 4 quarters or 1 period. So, the moving from Vmax to the first time where a is max or v is 0, it is a quarter of a period. So we need to find the period to find a quarter of it. Now we ask ourselves, how can the given data help us find the period? So you notice, solving the problem involved 2 sections, 2 parts. The first part, identifying what we need to find, which isn't always given and obvious. Second part is how to solve it. So as after we have discussed at the beginning, why do we need the period? Now let's calculate it. We know that Vmax is omega multiplied by x max. We know that A max is omega squared x max. Notice that we've dropped the negative because we are just dealing with values. Now dividing A max over V max, omega cancels out, x max cancels out, omega squared in the numerator cancels with 1 omega in the denominator, and we'll have omega here. And period equals 2 pi over omega. It becomes 2 pi, omega is in the denominator, so over A over V, which is 2 pi V over A. We are almost there. This is the period. Now the duration that we need is T over 4. It becomes simply 2 pi V over 4A, cancelling 2 and 4, or simplifying them, we get pi times V over A. Now jotting in the values, 3.14 multiplied by V max and A max here for sure, multiplied by V max, which is 1.82, and dividing the whole thing by A max, which is 4.30, we get, taking here, let's say 3 decimal digits, we get an answer of 2.65 something, 2.66, because we rounded up, seconds, divided by 4, which is 0.665 or 0.67. Now, depending on how many decimal digits we need, here is the answer, 0.665 seconds. Don't forget the seconds. And that's it concerning the first application. Application 2. When a force of 10 newtons is applied to a spring, it stretches by 8.75 centimeters. Determine the frequency of oscillation of a 3.6 kilogram body attached to its free end. So again, we need to identify what we're given and what we need to find. So we are given some information about force being 10 newtons and the corresponding elongation to be x being 8.75 centimeters. We know that it should be in meters, elongation and stretching should be expressed in SI as a meter, but there's no harm in keeping it in centimeters unless the value is going to be used in another calculation. We'll come to that later. We are also given, or the question in fact, is to find the frequency when a mass, okay, so this goes back to given, of 3.6 kilograms attached. So this is the given. We are given the force that produces some elongation. Then we are given a certain mass and we are asked about the frequency of oscillation of this particular mass. So how can things be related together? Now I'll change color and like brainstorm some of the equations that I might need. Frequency is angular frequency divided by 2 pi. And angular frequency itself is square root of k over m in the case of elastic pendulum as we have here. So I think we can directly say that frequency becomes square root of k over m all divided by 2 pi. Now m is given for this particular oscillation or for this particular question because the question demands frequency when a mass of 3.6 is attached. We lack only k. K isn't given. How can I find k? Now here comes my question. So I'm given the force and the elongation and we know that F equals kx, right, as values. Thus k becomes F over x where F and x are corresponding. So the force that causes this elongation and vice versa. And since k is going to be used later, so I have to change x from centimeter to meter as we discussed. So now we go to start solving. As you got used to, I do not use numbers while solving. We leave numerical application till the end. So we start first by Hooke's law F equals kx, in case you want to keep track of what we've done. Thus, k becomes F over x. We are given a particular value of f and a particular value of x, and that's it. I'll stop here. I will not write numbers. 10 over 0.0875 if you want to find it, etc. So let's keep it as k being f over x. Later on, if I find it better to evaluate it, I'll do it. After that, we go to frequency being omega over 2 pi. We can use this directly, which is square root of k over m, which is omega, over 2 pi. Here we notice that if we can replace k by a value, it's better than writing f over x. So you can go here to say radical f over x times m over 2 pi, or simply allow me to drop this. I'll go back to calculate k and then come back to continue this calculation. So I go back here, 10 divided by 0.0875, and the answer is gonna be, I'll erase this, 10, okay, so it's gonna be 114 point, let's say 3, okay, Newton per meter. So the unit here is, the units are base or are SI units in fact. So going back to frequency, it is square root of 114, which is k, 0.3 over 3.6 over 2 pi. Now jot that on a calculator and double check the calculation, and if I'm mistaken, please write that in the comments, and I'm gonna get an answer of 0.896. Now I need one decimal digit, let's say, so this is gonna be 0.9 or 90 hertz. So that's it. This is the answer for this application. Application 3. The position of an oscillator is given by x being 0.16 cosine pi over 3t. X is in meters while t is in seconds. What's the magnitude of its maximum velocity? Now, as we always do, we specify or identify the question. Here we need to find Vmax. Then we ask ourselves, what's the first thing that comes to my mind to find Vmax? What I thought about is the equation which we kept on mentioning while listing the equations of this part, Vmax being x max omega 0, or omega, where omega, the angular frequency, is x being x max plus or minus sine or cosine omega t plus phi, if you remember, right? So omega is the coefficient of t. So directly going back to solving, now I think I have a clear view of the solution. Vmax, in case you want to keep track of the solution, is omega times x max. Omega is pi over 3, the coefficient of t. X max is 0.16. So this becomes pi over 3 multiplied by 0.16. And the answer is gonna be 0.17, and Vmax is in meter per second. By the way, pi over 3, 3.14 over 3 is approximately 1. So 1 times 0.7 is 0.16, 0.17 is a very reasonable answer. That's all concerning this topic. Thank you for your time, and we'll meet again in topic 2 of this chapter.